We now understand the basic common source amplifier topology. It is the basic amplifier using the 2-port, but to set up the correct operating point for the transistor, we have some additional components which also appear in the small signal incremental picture and influence the gain. Okay. Now, we go back to the model of the MOS transistor. It turns out that we had omitted a particular detail of the MOS transistor, and that further reduces the gain. Okay. If you recall, the ID VDS or the output port characteristics of the MOS transistor, this is what we had. We had a family of curves for different values of VGS, and of course, for VGS less than VT, the current would be 0, and for let us say VGS of 2 volts. By the way, I am still assuming the same transistor that I have always been using in the examples, which is a transistor which has a threshold voltage of 1 volt and a current factor of 100 microampere per volt square. Okay. And we know that for a VGS of 2 volts, the current increases and saturates to 50 microamperes. Okay. This is VDS in volts, and also if I plot the ID versus VGS, assuming saturation region, in this case, which means that VDS is assumed to be large enough. Okay. We would get a parabola. This is in volts, this is in microamperes for a VGS of 2 volts, we have 50 microamperes. For 3 volts, we have 200, and for 4 volts, we have 450. Okay. And the output characteristics also for VGS of 1 volt, it saturates to 50 microamperes. For VGS of 3 volts, it saturates to 200 microamperes, and for VGS of 4 volts, it saturates to 450 microamperes. Okay. The key assumption here is that in the saturation region, that is to the right side of this curve, there is no variation of current at all with the drain source voltage. That is, all these curves are perfectly flat as we wanted for our amplifier, okay, to maximize the gain. It turns out this is not truly the case. The current does increase with VDS weakly though in this region as well. Okay. So, current increases weakly with VDS in saturation region. Okay. And if you attend courses on device physics, you will understand why this is the case. Okay. The saturation region current equation was mu n C ox by 2 W by L VGS minus VT square. Okay. This was for saturation, which is to say VDS more than VGS minus VT. It turns out that, like I said, there is a dependence on VDS, whereas this equation has no VDS at all, and that is introduced by an additional factor 1 plus lambda VDS. And you can see that as VDS increases, this entire thing, the current increases. Okay. And the units of lambda are in inverse volts, and this is typically a small number, let us say something like 0.05 inverse volts or something like that. Okay. So, that this correction is still usually small compared to 1. It also depends on the technology itself. We will not go into those details. As far as we are concerned, is lambda is an additional model parameter for the MOS transistor. Okay. And this correction factor appears only in the saturation region, okay, because the physical phenomenon by which this current increases is known as channel length modulation, and that happens only in saturation region. Okay. So, now if I plot this, what happens? The current obtained from this term, what I have shown in black is what I have plotted here. Now, to this I have to have a multiplying factor of 1 plus lambda VDS. What happens if I do that? In the saturation region, the current will increase slowly. Okay. So, that is what we get. This is including the factor 1 plus lambda VDS. Okay. So, this is the true characteristics of the MOS transistor. Now, you can quickly spot a problem here. I told you that this correction factor appears only for the saturation region and not for the triode region. Now, what happens is, you can see that the triode region remains as it is, and because at this point you multiply it by some number more than 1, because it is 1 plus lambda VDS. Okay. So, it appears that there is a discontinuity. Okay. But do not worry about it, the actual model of the MOS transistor is very sophisticated and complicated, and it does not have these discontinuities. It is because we are using oversimplified models that we have this problem, but that is okay. But we do need these oversimplified models for any hand calculations. Okay. So, do not worry about this discontinuity, it is not going to be there in the real MOS transistor, but we will use these models which do appear like they have a discontinuity without any problems. Okay. Because the purpose of hand calculation is to get an idea of what is happening. Okay. To get the exact answer, we will use the sophisticated model in a computer simulator, and that usually has hundreds of different parameters. Okay. So, the phenomenon by which this additional factor appears is known as channel length modulation. Now, if you do not look at the device physics, this term will not make any sense at all, but that is okay. All we need to know is in saturation region we have this additional factor, okay, and lambda is a parameter that is given to you, and it turns out that lambda itself depends on the length of the transistor. Okay. And this k lambda is some proportionality constant. Okay. Again, do not worry about exactly why these things come about. Usually in this course lambda itself will be given, or if it is given in this form, the k lambda will be given. Okay. So, as far as we are concerned, we have to model it in the correct way using this expression and possibly this one if necessary. Okay. So, this has some implications on the amplifier that we will look at by deriving the small signal model corresponding to this new model. Okay. So, this is the large signal model of the MOS transistor, including this additional factor due to channel length modulation. We will derive the small signal model and see what effect it has on the amplifier. Okay.